Welcome everyone to the live interactive session number 10 of the course Mechanics of Fiber Reinforced Polymer Composite Structure. Today I am going to discuss some sample problems related to assignment number 10. I am the TA for this course and my name is Ananya Mandal. So the first question is that a thin cylindrical pressure vessel is originally made of aluminium having density equal to 2700 kg per meter cube and sigma y equal to 250 megapascal. The cylinder has an internal diameter of 1 meter and it should be able to withstand an internal pressure of 1 megapascal. In order to reduce the weight, the cylindrical pressure vessel having the same radius now needs to be made from unidirectional carbon epoxy laminae with lamina thickness 0.25 mm and having a stocking sequence of 092S, that is 090 twice symmetric. The properties of a unidirectional carbon epoxy lamina are as follows, where we are already given the E1 value, that is 140 gigapascal, E2 value 10 gigapascal, G12 6 gigapascal, mu12 equal to 0.28, and the density is 1560 kg per meter cube. And also the ultimate strength of the lamina is also given to us for both tensile and compressive strength. So the question here is that neglecting residual stresses due to manufacturing, the minimum thickness of the cylinder in mm made from aluminium use maximum shear stress theory is. So according to the maximum shear stress theory, a material will fail or yield when its maximum shear stress equals or exceeds the shear stress value at the yield point in the uniaxial tensile test. So we can get the when the maximum shear stress value should be sigma 1 minus sigma 3 by 3. So from that we will get the maximum shear stress. So first we need the value sigma 1 and 2. So for that, the value sigma y is given to us for the aluminium cylinder, that is 250 megapascal. So from that, that is the hoof stress. So the hoof stress equation is Pd by 2h, where P is the pressure, D is the diameter, and h is the thickness. So the pressure is also given to us, that is 1 megapascal. The diameter given, that is 1 meter, and the thickness is what we need to find out. So keeping the thickness as h, we can get the value of the hoof stress sigma y equal to 500 into 10 to the power 3 by h in Newton per millimeter square. Now this is the hoof stress and we also need the longitudinal stress sigma x. So that is half of sigma y. So it will be 250 into 10 to the power 3 by h Newton per millimeter square. Now the principal stresses, that is sigma 1 and 2, can be found out by this equation by using the longitudinal and hoof stresses. So from that we got the value of sigma 1 as 250 into 10 to the power 6 and sigma 3 value is equal to 0 because we are considering that in z direction there will be no stresses. So sigma 3 is equal to 0 and sigma 1 and 2 values can be found out from this equation and we got, and for finding according to the maximum shear stress theory we need sigma 1 and 3. So sigma 3 is equal to 0 and sigma 1 is equal to 250 into 10 to the power 6. So putting that in this equation, yeah. So sigma 1 value is 500 into 10 to the power 3 by h. So that will be the value of sigma 1. And when we will put it here, sigma 1 value we will put as 500 to the power 3 by h. and 2 is already here, minus sigma 3 which is equal to 0. So this should be equal to the hoof stress. So the hoof stress value is already known to us. So from equating these two, we will get the thickness that will have, like, equating the original hoof stress and the hoof stress we will get according to the maximum shear stress theory. So by equating those two, we will get the what will be the thickness for the aluminium pressure vessel. Now with the same given data, the next question is that when the cylinder is made from 092S carbon epoxy, the percentage reduction in overall weight compared to the cylinder made from aluminium is. So the equation for percentage reduction in overall weight is given as weight of the aluminium pressure vessel minus the weight by carbon epoxy pressure vessel divided by weight of aluminium pressure vessel. So now for that we are already given the value of density. So density is equal to mass per unit volume. So to get the weight we need the density multiplied by the volume, as the volume is similar for both the aluminium and carbon epoxy pressure vessel. So we will use the density. So density of the aluminium is given to us 2700 kg per meter cube, and density of the carbon epoxy is also given, that is 1560 kg per meter cube. So we will use, instead of weight we can use the density. As you can see here, thickness is given, but thickness is same in both the cases, as previously we solved the thickness for the aluminium pressure vessel, and also the thickness given here for the carbon epoxy pressure vessel is 0.25 mm, one lamina thickness, and as it is a 2S, that means there are 8 laminas. So 090, 090, 090, 090. So there will be 8 total laminas. So when we will multiply 8 into 0.25, you will get 2 mm. So that's why the thickness will also be same in these two cases. So we can directly equate the density. So density of the aluminum minus density of the carbon epoxy divided by density of the aluminum, and from that we will get the percentage reduction of the overall weight. Now next question for the same given data is that when the pressure vessel made from 092S carbon epoxy is subjected to an internal pressure of 1 megapascal. So what will be the global strains induced at the top 0-degree ply? So these are given at the options. Now for this, first you will need the reduced stiffness matrix for 0 and 90-degree laminas. So for finding the reduced stiffness matrix of 0-degree lamina, you will need the values of E1, E2, G12 and mu12. So from this engineering constants, you can find the values of the constants in the reduced stiffness matrix. So from that you will get this Q bar matrix, reduced stiffness matrix for 0-degree. So as we have done already previously, that when we got the value of reduced stiffness matrix for 0-degree to make for 90-degree, we just have to change Q dash 11 with Q dash 22. So we will interchange those, we will get for 90-degree also. Now we need to find the A matrix. So previously we have already discussed how to solve for A matrix. So for the sequence given 092S, we have to find the A matrix, where 0 will be, there will be 4 laminas of 0 and 4 laminas of 90. So you will multiply 4 multiplied by the reduced stiffness matrix of 0 plus the 4 times the reduced stiffness matrix of 90 into also the thickness of each lamina. For 0 it will be 0, so both of them it is 0.25. So from that you will get the A matrix. Now we need the load. What is the load given to this pressure vessel? So load uh, load is the stress multiplied by the thickness. So from that you will get the as we previously done here, the hoof stress and the longitudinal stress. So the hoof stress, when we have to change it to load, we just have to multiply it with the thickness. So hoof stress multiplied by thickness, you will get the load in y direction, that will be 500 into 10 to the power 3, and longitudinal stress is sigma x. When we have to convert it into the load in x direction, nx, then we have to multiply it with the thickness, so it will become 250 into 10 to the power 3 Newton per meter. Newton per mm. So you have to convert it to Newton per meter. So from that we got the value of nx and ny. from this equation of hoop stress and longitudinal stress? So they have asked in the question to find the global strains induced on top 0-degree ply. So to find the global strain, we have to first find the mid-plane strain. And the equation for mid-plane strain we know is equal to A matrix is load equal to mid-plane strain multiplied by the A matrix plus the B matrix into the your curvature. So the B matrix is already equal to 0 as it is a symmetric. So only equation we will need here is to find the strain is equal to the inverse of A matrix multiplied by the load. So load values we got from the stress hoop and longitudinal stresses. So we will put those values here. We have to inverse the A matrix. The A matrix we already got, and from that we will get the mid-plane strains. So these are the values of mid-plane strains. Now mid-plane strain is equal to the global strain plus the thickness into the curvature. As no curvature value is given to us, so we will consider that the global strain is equal to the mid-plane strain. So for all the plies, the global strain is equal to the mid-plane strain. So as they have only asked for the top 0-degree ply, so mid-plane strain we already got. That will be the same for the global strain of the 0-degree ply. So this will be the answer. So after solving this, we have to choose the option which will give this answer. The next question is that when the pressure vessel made from 090 2s carbon epoxy is subjected to an internal pressure of 1 megapascal, the material axis stresses induced in the 90-degree plies in megapascal are. So in the last question, for the top 0-degree ply, they have asked for the global strains. Okay. So in the last question, we have already solved this whole the same with the same data till we find the global strains. Global strain for top 0-degree ply, but since there is no curvature, so the global strain will be equal for all the plies. Now they have asked here to find the material stresses at the 90-degree ply. So the first thing is we have to change the uh, global strain to material strain. So for that we will use the transformation matrix to convert it from this global strain to material axis strain for the 90-degree ply. So the first step we got epsilon 1, epsilon 2 and gamma 1, 2. So these are the material axis strains at the 90-degree ply. So after converting to strain, we just need to convert it to stress. So for finding the stress, we will use the reduced stiffness matrix for the 90-degree ply. So the stress is equal to the reduced stiffness matrix multiplied by the material axis strains. So from multiplying these two matrices, we will get the final material axis stresses for the 90-degree ply. So that's why these all questions are interrelated because one data from one question can be used for the next question. Like this last question that using the maximum stress criteria, the factor of safety of the pressure vessel made from 092s carbon epoxy laminate and subject to an internal pressure of 1 megapascal is. So as we have already done in the last session also, we have to find which ply will fail first. And from the ply which will fail first, we can get the factor of safety. So from the last question you can see, we already found the stresses for the 90-degree ply. Similarly, we have to find the stresses for the 0-degree ply. So for 0-degree ply, the strain is known to us, the global strain, that will be the same as the material strain. And from that material strain, by using the reduced stiffness matrix, we will get the stresses for the 0-degree ply also. So now for 0-degree ply and 90-degree ply, we have the stress values sigma 1, sigma 2 and tau 1, 2. So from these stress values, we have to divide it with the ultimate tensile stress values in both this direction, in longitudinal direction and transverse direction. So sigma 1, we have to divide it by sigma 1 ultimate in tensile value. So this value divided by 2400 megapascal. Similarly, when you will equate them, we will get the stress ratio. The stress ratio 1, stress ratio 2, stress ratio 3. That is talking about the sigma 1 value, sigma 2 value and the tau 1 2. Then we will know which ply will fail first by seeing which value is the highest. So here you can see this value is the highest one among all the 6 values. So this is the one which will fail first. So we got the ply which will fail first. Now that ply will give us the factor of safety, as factor of safety is nothing but the inverse of the stress ratio. So first you will get the stress ratio of the ply which will fail first, and then you will inverse it, and from that you will get the factor of safety, that is 1.348. So next question is that a thin cylindrical pressure vessel with an internal diameter of 1 meter is made of 0.25 millimeter thick graphite epoxy plies, having a stocking sequence of 0, 45, minus 45, 90 symmetry, and needs to withstand an internal pressure of 0.5 megapascal and a twisting moment of 157 kilonewton meter. The reduced transform stiffness matrix for the plies are given as. Reduced stiffness matrix values are given. So we have to find the global axis strain in the 0-degree ply. So already we have done these kind of questions before also. So this is the same thing, but here not only 0, 90, we have 45 and minus 45 also. So we are already given the reduced stiffness matrix for 0, 90, 45 and minus 45. From those values, we have to find the A matrix. Now A matrix here, this symmetric, so all these angled laminas are twice. So you will do 2 multiplied by the reduced stiffness matrix of 0 degree into the thickness, that is given as 0.25 mm, plus 2 times reduced stiffness matrix of 45 into the thickness 0.25, plus 2 times reduced stiffness matrix of minus 45 into the thickness, plus 2 times reduced stiffness matrix of 90 degree plus the thickness into thickness. So that whole summation will give you the A matrix. So this is the A matrix. So first step is to get the reduced stiffness matrix. Second step is to get the A matrix, because as it is symmetric, B matrix will be equal to 0. So the equation for strain will be the load equal to A matrix into the strain. So now we need the values of the load. So Nx and Ny value.
Ma'am,
Yes.
this A matrix how we can get?
A matrix we have like how we have solved in last two exercises, last two sample sessions we have done, right?
Right, right. Same type, ma'am.
Same, that
Same,
whole equation where you
same
have to
method.
do the summation of all the plies,
Yes, ma'am.
stiffness matrix multiplied by the thickness. So that from that equation only you will get the A matrix.
Okay.
So last two classes also we have discussed how to get the A matrix. The same thing. That's why I didn't write the equation here, because I thought you will be knowing by now that how to get the A matrix. Okay, so first you get the A matrix. Next is you need the values of the load. So load value Nx and Ny value can be you can find from the hoop and longitudinal stresses. So the equation for hoop stress and longitudinal stress is given. So for longitudinal stress is PD by 4S, where P is the pressure, D is diameter, H is the thickness. So from that you will get the sigma X. Sigma Y hoop stress you will get PD by 2H, and then here also given the twisting moment. So from twisting moment you will also be getting the shear stress. So shear stress is given as 2T by pi D square H, where T is the twisting moment. So from these stresses, we will get the load. So load is nothing but equal to stress multiplied by the thickness. So for Nx, it is sigma x into h, Ny is sigma y into h, and for nxy, it is 2t by pi d square. So these are some equations you need to remember. So from that we will get the nx, ny and nxy values. Now as there is no value of curvature given, so the midpoint strain will be equal to the global strain. So the midplane strain is equal to inverse of A matrix multiplied by the load. Load values we already know, A matrix we already got. From that we will get the global strain for the 0 degree plane. So midplane strain will be equal to the global strain, and that will be same as for the 0 degree plane. So from that we will get the values. The next question for the same given conditions, they are asking what will the material axis strains in micrometer by meter in 90 degree plane. So here they got the global axis strain of the 0 degree plane. Now they are asking the material axis strain of the 90 degree plane. So as the global axis strain will be same for all the plies, so just we have to use the transformation matrix and multiply it with the global axis strain, and from that we will get the material axis strain. So the transformation matrix we have to use according to 90 degree ply, multiply it with the global axis strains, and from that you can directly get the material axis strains from this equation. But always remember, when you are transforming from material to global axis, global to material axis, then this gamma 1 xy by 2 and gamma 1 by 1 gamma 1 2 by 2 value should be there. So according to that you can change from global axis to material axis. The reduced transformed stiffness matrices for the graphite epoxy plies are given as already given. So note, for a composite drive shaft, TB value is given. So each symbol has their own significant meaning. A hollow composite shaft of 1.48 meter length is made of 0.45 minus 45 90 symmetric laminate having 0.25 mm thick plies and with its outer radius of 50 mm. So considering a factor of safety of 3, if the shaft needs to transmit a torque of 18 Newton meter, the shaft will. Options are A. Buckle as the critical torsion buckling torque is less than design torque. Option B. Not buckle as the critical torsional buckling torque is more than the design torque. Option C. Not buckle as the critical torsional buckling torque is less than design torque. Or option D. Buckle as the critical torsional buckling torque is more than design torque. So here, two things we need to know: what is the critical torsional buckling torque and which is the design torque. Okay, so first step is to find the D matrix, because here they are talking about uh, moment, and moment is related to the D matrix. So moment is equal to the D mat. Moment is related to the B matrix and D matrix, but here as the symmetry there will be no B matrix, so here we have to consider the D matrix. So first we have to find the value of D matrix for the given laminate, that is for 0, 45, minus 45, 90 symmetric. So D matrix equation is also known to us, like similar to A matrix. Here only it will be equal to 1 by 3 and summation of the reduced stiffness matrix into the position of the lamina and their cube. So check, I didn't write the equation here, but we already know the equation as we have discussed previously. So from those equations you will get the D matrix. Next step is to find the Ex and Ey value. So the Ex value is equal to 12 by D11 star into H cube, and Ey is equal to 12 by D22 into H cube. And step 3 is the outer radius is given as 50 mm. Thickness of the laminate is also known, that is 2 mm, because each lamina is 0.25 mm. So inner radius will be equal to 50 minus 2 mm, 48 mm. Therefore, we will get the mean radius that will be equal to 0.049 meter. And we have to use this mean radius in the equation for the uh, so this equation is used to find the critical torsion value. And the torque which is given to us gives us the design torsion value. So we have to first find the value of TB, and from the value of TB we have to equate if TB value is higher than the what is the actual design torque. So torque is given 800 Newton meter. The factor of safety is given, that is 3. So the design torque will be 3 times of this, that is transmitted by the shaft. So we will multiply 3 into 800. So that will give you the design torque. Next is to find the critical torque. So critical torque, from this equation you see the values you need is Rm, Ex and Ey. So Ex, Ey values we got from this equations. For that we need the D matrix, and Rm value is the mean radius, which is equal to the outer radius plus inner radius divided by 2. So you got the Rm value. So put this value of Rm, Ex and Ey in this equation. From that you will get the critical torsion buckling torque. Then you have to equate this TB value with the design value considering the factor of safety and see which of that is higher. So here by equating this you will see that the your critical torsion buckling torque is higher than what is designed. That's why you're saying the option B is correct, that it will not buckle as the critical torsional buckling torque is more than the design torque. Okay, so these are the steps to solve this question. So for, only the equation is already given. So we have to find this equation value and then compare it with whatever is the torque value for the designed shaft. And from that we can answer whether it will buckle or not. Okay. So any doubts? Any doubts in the question? Somebody asked about the A matrix. Is it? Are you comfortable with that, or should I explain again how to get the A matrix from previous PPTs? Yes, Hari. Do you have any doubt?
No, ma'am, clear on A matrix, ma'am, no problem.
Did
Ma'am,
you
A
solve?
matrix, how we can get
Okay,
A
okay.
matrix.
A matrix. I will explain. Do you did you guys solve this assignment yet?
No, ma'am, hereafter only, ma'am.
Okay. Okay. So if you don't have any
Ma'am,
doubts,
have
then
a doubt in, ma'am, have a doubt in another question.
you can ask. After, if you have any doubts, then ask. Then I will again open my previous PPT so that I can explain how to get the A matrix. Uh, will you be discussing the doubt now, or should I start with like, okay, okay. What are the options? Hari, can you uh, the global stress?
What they asking is they asking about which one is true false. What I'm saying is the global stresses and the global strains, the both will be different orient parameter. I'm right.
So, see, the first thing how to tackle this question is see what is the laminate structure. So, it is symmetric. So, first thing is B matrix will be equal to 0. You will get a certain A matrix. Okay, so A matrix is the combination of all the laminas. So, from that you get the load is given, A matrix is known, you will get the strain. That strain value will be equal to the global, so global strain for each ply will be equal to the mid plane strain because there is no curvature. They're not talking about curvature. So from that you get that the global strain will be equal for all the plies. So option B, that is saying the global strains for differently oriented plies are different, will not be correct because the global strain will remain same. But the global stresses will be different because global stress depends on the reduced stiffness matrix. So reduced stiffness matrix for all the plies will be different. So that's why the stresses will be different, but the strain will remain the same for all the plies. So from that you check which option will be correct. So the global strain of differently oriented plies are different. So that is not correct. And the global stresses of differently oriented plies are different. That will be correct. So option B will be
So
correct.
the global strains of the different oriented planes will be different.
No, no. Global strains will remain same. Global strain will remain same. Material axis strain will remain different.
But you have said B is correct.
No, B is not correct. B is false. A is the correct one. I said option B is the correct. Option B, you see, statement A is true and statement B is false. That's what I was saying. That option B is the correct one. Like the questions we solved, as you can see, today also we solved. We found out the strain values. Like this question, you see the mid-plane strain value we got and global strain is equal to the mid-plane strain since no curvature. So whenever there is no curvature, the mid-plane strain will be equal to the global strain. And global strain will be same for all the plies. As you are not changing global strain with respect to the angle, it is remaining same. If the global strain was not equal to mid-plane strain, at that time it would have been different for all the plies. But if there is no curvature, then the mid-plane strain will be equal to the global strain, that will be same for all the plies. But when you go for stresses, then the reduced stiffness matrix come in the play and you have to multiply it with that. That's why it will be different.
Okay, ma'am. Okay, ma'am. Thank you, ma'am.
Okay, so as you have asked about the A matrix, how to get the A matrix. So in the this session number 8, I discussed, like you can see for this question. So in this question, they're saying 090 symmetric is the laminate. That means they have 0 lamina and 90 lamina, and then there is symmetric, that is again 90 0. So it is 0 90 90 0. That means there are two laminas of 0 degree and two laminas for 90 degree. The Q matrix, the reduced stiffness matrix, is given that we are considering for the 0 degree. So for 90 degree, the reduced stiffness matrix will be almost same, only the Q11 and Q22 values will interchange. So that will give you the reduced stiffness matrix for 90 degree. So from that, we can get the A matrix. Uh, So this is the equation for A matrix. Okay. So A matrix is summation of all the laminas for the product of the reduced stiffness matrix into the thickness. So Zk minus 1 is actually the thickness of each lamina. So from that equation, here you can see it is 2. 2 because there are two 0 degree and two 90 degree laminas. So for 0 degree first. So 0 degree, this is the reduced stiffness matrix. And we are seeing that there are two laminas of 0. So that's why 2 multiplied by the reduced stiffness matrix multiplied by the thickness of the 0 degree lamina. And it is already given that each lamina thickness is 0.1 mm. So, and also you have to take care of the units. You keep the units in the uniform one. Plus, because we need to do the summation of all the laminas. So, plus 2, because 90 degree laminas are also 2 of them. So, 2 into the reduced stiffness matrix for 90 degree lamina. So 90 degree lamina, the reduced stiffness matrix will remain same, only this Q11 and Q22 value will interchange. So in place of Q11 it will be 10, Q22 will be 200. So this is the reduced stiffness matrix for 90 degree lamina. So 2 times of reduced stiffness matrix for lamina 90 degree multiplied by the thickness of that lamina. So from this summation you will get the A matrix. So similarly you have to do for similarly you have to do for this question A matrix. Here they are saying, so here the stocking sequence is 092S. That means there are four 0 degree laminas and four 90 degree laminas. And also the reduced stiffness matrix we have to solve from E1, E2, G12 and V12 values. So from that you will get the reduced stiffness matrix for 0 and 90. And then you have to multiply the 0, 1 with 4 because there are 4 lamina into the thickness of the lamina plus reduced stiffness matrix of 90 into 4 into the thickness of the lamina. So from that whole thing equation you will get the A matrix. Okay, was I clear? Uh, Mohammed Alam, I think you asked that doubt, right? So was it clear? Any doubts in that?
Right, man. Clear, man.
Okay, so in previous assignments also you must have done to find the A matrix, right? It's the same.
Yes, ma'am, but I didn't understand, ma'am.
So did you understand now? Like, do you have any doubts with what I explained right now?
No, ma'am.
Okay. So do you have any more doubts? Mohammed Alam, do you have any other doubts?
No, ma'am.
Okay. Hari, do you have any other
Um,
doubts?
shall we get any last year or the previous year question papers or anything like that? Practice.
I don't have access to question papers. You can ask in the discussion if they can help you with anything. Sir might be able to help, but I don't have access to any question papers or exams.
Okay, okay. What we are doing
Ma'am,
is for
ma'am,
exam
in
point of view,
final exam,
which all.
A final exam related doubts, please ask in the discussion. Then sir will be able to answer because sir is the one who will be preparing the questions and all. I don't have access to final exam questions, question paper or anything. So
but
you
for
can
the final exam, you also concerned, ma'am, for making the question paper like that.
no.
Like
I'm only here to like help in solving the assignment. Final question paper decision, everything sir will take. So if you have doubts, you can ask in the discussion for this course. Sir will be able to see and answer this.
Okay, ma'am. Okay, ma'am.
Okay, then I will end the session here. Thank you.
Okay, ma'am. Good night, ma'am.
Good night.